Okay, so we will today look a little more closely at noise in CT images. And we're spending some time on this because it's going to affect how we analyze images. And it's basically affecting quality of the results. And in the processing that we're going to go through segmentation and learning about filtering of images, segmentation, and so forth. We have to have to deal with this noise. So we're going to spend a little more time looking into it, and we'll have an exercise today in Image J looking into the noise. I have just before coming to the classroom posted a link to data, but we'll get to that in a second. So let's get going. So noise in CT images. In a perfect, if we were imaging a homogeneous example and we got an image, one slice through it, then technically we should get an array of values that are all the same, except that we don't live in the perfect world. So first things first, homogeneous is relative, especially in porous media. Because as you zoom in, you will see some different structures, and it's these structures and pore structures and whatever mineral and fluid phases I might have in there, they average to this average value of a pixel or voxel. However, even if I actually had something that is uniform down to molecular scale, such as a beaker of water, I would still have some noise. And that noise comes from the imaging process itself. So ideally, I would like to get this, and then I'm going to say, oh, this is all the same phase, say water in this case, but that's not necessarily the case. What you actually get is that overall, you have the mean value that is kind of similar everywhere, but you have definitely variations. So this is an example. If your CT number ranges up to thousands, right, this is not a large variation relative to that 1,000, right? But it's all around 0. Minimum is -4, maximum is +4. So we'd like to somehow try to evaluate that. Why is that there? We've already went through how X-rays interact with the material. But there's the how X-rays interact and the fact that they emit a scatter of waves, right? And then I'm trying to detect those waves that have scattered off, that have either passed through or scattered off the material. And the detection process itself, we're not going to go into details, but you're basically you have certain photons that are coming in with a certain energy, and they're getting converted into optical photons, right? And that conversion process that happens in cameras or whatever is recording it's a statistical process, whatever I capture, but it's not perfect in itself. So basically, when you have this interaction with the pixel on the detector, then you're going to record something here, and it's this in this process of recording, there might be some noise. Now, the better your flux, the more photons you have, the more certain the value. So if you don't have enough flux, you will have more noise because of that. Okay? So some part of it we can basically correct after the fact, but it's the best actually if you correct the process of capturing this image as much as possible. Okay? So contrast is being able to capture difference, the difference between two materials. So let's say that I actually have slight noise here in this. Let's say that this is that water phase, and I have some other bubbles of, this could be emulsion, for instance. Okay, so I have those bubbles. Depending on what is the density difference between this fluid here And let's say that this is a fluid as well. I'm actually not certain what was imaged here, but I'm just going to go with that water story from the previous slide. Okay. Then I would like to basically be able to capture the difference here. However, if the density difference is not large, I might not be able to do so. And if I have an increased level of noise, those emulsion bubbles are still in there. I just might not be able to see a good contrast. Okay? And this is what we're essentially dealing with. So contrast is a measure of how well a feature can be distinguished from the surrounding background. I can inject my fluids with certain higher, like for instance, if I have water and oil, their contrast is not good, but I can inject one of them with, for instance, iodine or bromine to increase that contrast. And then I'll be able to detect them better. So basically this contrast is effective difference in attenuation between whatever I want to image as a feature and the background, and divided by the background attenuation. So that is sort of a difference. And the ability to discriminate two with closely similar linear attenuation values, which basically translates to similar density materials. It depends on the accuracy with which you can actually determine this attenuation. So technically, if you had an object and a background, and let's say that they're both homogeneous, as you kind of walk through, like, let's say we have an imaginary line here, I would want to have sort of, this is my background, this is my object, and this is my back to the background. So this is what I would hope to get as I draw a line through. Well, good luck with that. What we really get is something like that, this. So basically, I might have a very good contrast between the two. This depends on the materials themselves. So that's basically this difference here. And I have some noise associated in both, with like an area here and an area here, but I'll be able to deal with that noise, right? I can easily sort of draw a line through this and line through this and still differentiate these two really well. So this is a case where I have a high contrast case, and my noise relative to this contrast is low. Okay, so I have a little low noise up here. Now, even if I have higher noise, as long as I have good high contrast, I will technically be able to recover from this as well and still distinguish this object from this background just fine. However, if I have low contrast with low noise, I'll be able to recover, but basically with a high noise, that noise, its amplitude will simply swallow the contrast, and I won't be able to get a good image. Okay? Now, the smaller the object, unfortunately, the worse it is. So if I have the same situation, just a smaller object, I'm going to kind of lose it to the noise. And that's part of that. This is that here I sort of show the values, but there's a little bit of a spread function here. This is due to it's called point spread function, and it's due to the finite spatial resolution. Okay, so there's a little bit of what you should be a sharp edge, even if I had noise. It kind of spreads and lowers a little, and that can basically eat up a smaller object if the object size is within the width of that point spread or the so that's what's actually effectively happening here. Even though technically it was the same object and same background as in this case. So smaller features, they basically, and we will look into that once we actually start trying to segment those small features and distinguish them from the background. So basically, as you go across, if this was indeed an emulsion, your smaller bubbles, the the difference, this contrast across from smaller bubbles would be smaller than it is. So the difference between CT values across smaller objects would be smaller than it is for larger objects, even though you have the same material in the small object. Let's say that you have an emulsion with small bubbles and large bubbles. Those bubbles are the same phase. Surrounding the bubbles is the same phase. But when you image them, you will have sort of a smaller jump across smaller bubbles than you do have across larger bubbles. Okay? Same thing goes for thinner fractures versus thicker fractures. Okay? And we will exercise those a little, like we will actually see the exercises of those. But those are often the important features, and I don't want to undercount them. Okay? So it's a problem to basically that we have to deal with. Okay? So in this case, none of the low contrast cases I can actually get a good image of. Okay? So signal to noise ratio is one way to sort of define the contrast, and it's often used to evaluate these cases. And signal is simply here the total measured count of something, and that is correlates with my attenuation in the image. So basically the way you look into this is like if you want to inspect the situation, you kind of find your subregions, so here within one object and the other object, and basically do some statistics on the values within here and values within here to see what the variation is, so that you can get sort of the amplitude of these variations, and then you can actually measure them across. So the important part here is to, when evaluating here, to stay within the object of interest, to stay on the side of this separation where you are. So let's actually do that. So basically, you compute the mean and the variance of the pixels in two different regions, right? And then signal to noise ratio is the difference in these attenuations, or whatever the tomographic values are, and divided by the variances. So let's actually do that. So I sent you a link to get a sample, and this is a sandstone. It's Benheim sandstone. And we can see grains, and we can see pore spaces. So this is a 16-bit unsigned image that we're going to import. Oops. And it's a little Indian. That's important piece. But you can practice what you get if you try big Indian and little Indian, right? Never enough practice of that.
When you say you send us the link, that's on
in Canvas. Yes. Data for today. This doesn't come across as link, but you can copy it nevertheless. And let me know if it should be activated so you can download, but there's lots of files, so I'm gonna open the same myself. So we're gonna, whoa. Oh, hi. Could not determine. Am I online? I should be online. Import raw. So I'm gonna go now with you to the same. Where is my box? Ah, it's on desktop. So on my box, PGE. So take the one that is UBO best. It might actually have .raw. So I'm gonna open. So this is 200 by 200 by 200. And it should be like that. There we go. So it's Benheimer.nx200 ny200 nz200.ubs. Or possibly it's showing up as also .raw. That kind of depends on a computer. And it's a 16-bit unsigned little endian. And if you do plus, that will enlarge the image. Now, I pointed out that the histogram is one of the important things to look at. So we can just quickly look at the entire histogram. And you can see some of the separation of the peaks. And good separation of the peaks also shows you a pretty good contrast. Okay. So technically what you're looking at, there's a mean value here and a mean value here. Those are effectively the mean values within each region. You just can't use what it gives you here because here the assumption for this statistic here is that this is normally distributed, which it's not. It's binormal. So really a proper correct way to do this would be to fit this as a binormal distribution, this histogram. And then you would have a mu1, mu2, right? And you would also have sigma associated for both of these standard deviations. And then you plug them into the formula I gave. That would be super effective way or the proper way looking at the entire image, right? But for just this particular exercise, take a little subregion within here, and you can isolate it in any way you want, maybe like this rectangle. Okay. And try to find what these values are within. Okay. And there is a little nice feature in ImageJ, which is also why I like using it in situations like this. You can kind of quickly click around the image and explore, which is valuable. So you draw a rectangle, and in analyze set measurements, you add standard deviation. So whatever it is that you can draw as a separate object, you can then kind of analyze within it. And you can get the area of it, you can do mean values, you can do standard deviations, minimum, maximum, so you can explore. So grab two regions, one of them within a grain and one of them within a pore, and do these measurements. So I'm gonna work with you. So here I grabbed there's analyze, set measurements. So here, this is everything that you can try to measure. So if you were actually analyzing emulsions, you could try fitting ellipses and whatnot as you go around. Figure out diameters, median, you name it. So what we are really interested in is like minimum and maximum, area, and standard deviation for this exercise, and mean. Okay. Okay. And now I'm gonna then do measure, and it's gonna give me the measure of that. So in this area, this is how many pixels I have. This is the mean value within, standard deviation, minimum and maximum. Whenever image J is measuring something, it has this results table, right, as sort of a default place to go to. You can actually save this table, save as, and if you save it as a .csv file, you can read it into Excel and do measurements somewhere else as you please. Okay, and now I'm going to go to another, so draw another rectangle right here. I can try to be larger, just trying to stay within the poor values. What on earth is going on? Is this a happy Wednesday outside? And if I do analyze measure again, I'm going to get measurement. So this is a little smaller rectangle. And I have smaller mean. So I have a jump of about 3,000 here, right? My standard deviation compared to within both is around 250, so I'm dealing with a similar type of noise in both areas. But 250 compared to 3,000, right, is still discernible, right? So I have enough. And you can see that kind of this is supposed to be the same mineralogy or very similar. And this is empty, and I see quite a bit of noise, right? And basically, you can take this difference and divide it. So when I did these slides, I had slightly different averages of values because as you move around, you get slightly different values. But this is just as a first order kind of moving around your image and finding out. And of course, I have totally avoided this clay here. There's a third material sitting in here. Okay. All right. So this is signal to noise ratio, which is pretty good. So I can distinguish these grains and solids pretty well. Yes? Okay. Again, if I did a histogram, this was slightly blown up when I was doing it. We can already, technically, if I fitted a distribution here and get the mean of each of these peaks and standard deviation of the peaks, that would be a little more robust measure going over the entire image. Yeah? Okay. So we will now look into some other. So now I also have the spatial resolution, and it's the balance between the spatial resolution and the size of the image or the feature I'm looking at that can sometimes swallow the feature, right? So that's something to have in mind. This is sort of the level of the details that we can actually resolve. So it's typically the smallest separation distance for which I can evaluate attenuation values between 2 points as separate, okay, and accurately get accurate statistics on those two close locations. And this is something that is affected by the voxel size, that source spot size, if I have a point source, if you remember. Any kind of issues that I have with the detector, blurring, signal to noise ratio, and number of angles depending on the geometry that I'm doing. I might have a cone geometry or a parallel beam. Either way, I have to rotate the image a number of times, and there's a number of times I do that and record an image. And how many of those angles that I'm actually using to recover the scan matters. Okay, so you can actually see the difference. This is basically the low number of angles used to recover the image. So there is more blurring resulting if you don't have enough information. And you can see that in histograms. So when you get a histogram that looks like this, they're still sort of the same, and our eyes tend to see the same. But our eyes are much more tolerant than the numbers actually are, right? So, so then the problem is that if you have, so this is simply a resolution issue. So I've averaged more, and my pixel size is larger, so I'm averaging more within each volume, and that will kind of blur the difference between what is here a well-distinguished peak at the lower end and this peak at the higher end. Okay. And also, how much of a feature do I have? You can see that here, pore space, this is a sandstone, so this is 20% of the space, right? Versus 80% of the space. So I have no trouble seeing this peak no matter what, but this peak of 20% of the space could be swallowed simply because I have less of it. So of course it's also thinner in places. Yeah? And then this lower resolution kind of swallows a lot of it. Yeah, overcomes. So histogram is often a quick look at whether I have a good quality separation. However, I do also have to know what I have or what it is that I'm looking for. If I want to identify these things, they're kind of harder to see in histogram because volumetrically I don't have a lot of grains like this. So this is another mineral phase. And technically it should be in this, that's somewhere here, I'm guessing. Okay. It doesn't really appear in the histogram simply because I don't have enough of it volumetrically. But it's actually well distinguished here locally. So I don't think you can ever, the point I'm trying to make is that you do have to look at the image in front of you and a statistical measure that basically is just the statistics for the entire image, which is something histogram. So both have to be looked at in order to kind of to evaluate what it is that you have. And you also need to know what it is that you're looking at, which can be a cat and mouse game. If you're looking at something that you're trying to find what the mineralogy is, so you don't know how many phases or what it is that you're going to call a phase inside your image, then you're guessing, do I have 5? Do I have 7? Do I have 3? Do I have 2? Right? That's what becomes problematic because this is your view into what you have. Right? So having additional information is often important. And in this case, what one supplies X-ray with is with some sort of microscopy image or X-ray diffraction that can give a more details on mineralogy that is actually seen in the slice. But that is different type of imaging technique. Okay, and often they have to be used together. Yes.
So in this image on the right, we have a resolution of 10 micrometers.
Mm-hmm.
This means that at a distance of 10 micrometers, we can distinguish between two attenuation values.
Right.
And can we determine this resolution within the software? It's
No.
an equipment limitation.
Okay, so this is something that has to travel separately. so image itself does not contain. Ultimately, this image, if I don't tell you that it's 10 micron, you don't know, and there's no way you can know. Okay? So image becomes sort of an object on its own and has some almost like a life on its own. You have to know what the experiment was and what it is that you physically put into the imaging device, right? Including what were the parameters of the imaging to know the. So you have to talk to a person taking the image, and they have to give you that information. You have to talk to Javier. But I'm laughing, but I'm not laughing because that image, that information can be easily lost. Right? If somebody didn't write it down, if it's not put in the same folder, right? And often we ultimately carry on and we analyze and we forget about it. Right? And what is also, there's file formats by themselves. They differ from the imaging facility to imaging facility and how they store the information. So I don't know what Javier does, but I know that if I go to UTCT, they give me a Word document that has information on X-ray energies used, the resolution and all that. That's just like a big file. Out of it, I really recognize 3 or 4 things in there. There's a whole bunch of parameters that I don't even know what they are because I'm not the person sitting doing the imaging. But they know, so if you come back to them and say, I don't like the contrast that I'm seeing here, can you try different X-ray energies or something to improve so that I can see my small emulsion bubbles or whatever it is that you're looking for in an image, right? So this is where I'm advocating, like you kind of often have to work with the person doing the imaging to get good contrast to see what you need to see. Okay? And comparing different images at different resolutions, at different X-ray energies, all helps. But ultimately, there might be simply limitations in using X-ray, and you need to go to microscopy and supplement that information. So always look for extra corroborating information. I think that's true for research in general. Okay. So, but those are certain issues. Now, there is issues that we mentioned already with beam hardening. Okay, so if I have a polychromatic beam, meaning that it's a composition of different electromagnetic waves and it has both hard and soft X-rays within, then different X-rays will interact with your material differently. And soft ones are attenuated more as you're going through. So as you're going through, traveling through the middle of the sample we'll see a filtered beam, okay? Because the whole point is that some of it is attenuated. So basically, it's lost more soft X-rays than hard ones, so that's why we're calling it hardening. Okay? And some part of the samples are basically probed by different types of beams, but I don't know that when I'm or I don't take that into account. If I don't take that into account while reconstructing the image, I'm going to have different grayscale values mean different things in different parts of the image. And we are taking, all we are left with when we have an image is these grayscale values, right? So there will be something, it will look like this. Okay? So your eyes see the contrast, and you have good contrast pretty much everywhere here. However, this gray right here and this gray right here, even though they're both in the void, they're not the different level of gray. And if I'm applying an algorithm that is processing the entire thing, I'm going to have hard times recognizing phases here, even though my eyes are kind of saying, oh, this should be fine, right? Because local contrast is fine. So this beam hardening correction is hard to do unless you know what you're imaging. So a lot of times the different X-ray facilities will do enough tests with known samples. Oh, I put a cylinder of aluminum and outside of it something else, right? And if I know what I'm imaging, I can do these corrections. With porous materials, that's a little harder. And with porous materials, it's never going to be exact game. Okay? So I'm going to use so basically there is corrections that you can simply do by comparing the data. And those corrections can be applied to all of the images afterwards. But they're not going to always work perfectly. So that's something that you have to take into account. Right? So this is an example of corrections done. Now, which one's corrected? Which one is not corrected? It's a little hard to see. So this one has beam hardening, and this one has less of it. So you typically see it as a shade, like a change in shade on the outer side of the image. Okay? Now, another part of the problem is the detector pixel, just like on your screen sometimes, the detector or the screen pixel can die. Okay? And because of that, it's going to cause sort of like a line through the image, right? But it's going to, you can see it sort of consistently in all of them, right? So one bad pixel will trace a circular path because you're rotating images you're going through, right? And that you will see something like this is a bad pixel. And it's common enough, again, because the detectors have to have very fine resolution too, and that's hard to execute, right? There's a physical material that is converting your X-ray beam to a photon level or optical image, right? And that conversion happens because of the material properties in the pixel, which have to be in the physical, they have to be in the same resolution that you want to get. Yeah.
So in this image we have so many ring stresses, a lot of pixels are basically damaged.
Yeah. And it might be hard to. Now, this is also sometimes corrected before you get the image. Right? So this is, if you correct with software image, you're just gonna smear it. So if you correct it after the fact, there's smearing. But with hardware correction, so apparently if you just basically move the camera around and collect more images, then you are able to recover. But that's what basically physicists who do who study imaging itself and how to reconstruct the images, they can correct it the best. So the point of all of this is that it's best if you actually have hardware corrections or additional images taken that can make up for these problems that will inevitably show up. But nevertheless, sometimes you actually have to go with this type of correction. Okay, and hopefully survive it. Yeah, So if you have that ring artifact that looks like a ring, when you look at it so this is a ring, right? So it's cylindrical. So when you look at it in the vertical cross section, you're going to see this. That's one bad pixel going through. Okay. Finally, one thing that we're assuming when we are imaging is that things are static for the amount of time that it takes to collect good statistics on the image. If I have glass versus sandstone, those are two different times, right? So basically, if I have something that is relatively easy to image and easy to pass through, then I need shorter time, and things need to be static for the shorter time. With fluids in porous medium, whether they're equilibrated is not always something known on the outside. So you could have fluids moving either because you're physically moving something or they just haven't equilibrated, even though you've been pumping for a while the same steady state on the outside. but inside, internally, there might be motion of the fluids and displacement. And when they're moving, then you get some sort of like shades of things moving like that. So if you actually want to collect these images in time, okay, you have to have some it's getting tomography in time is difficult because of that, if you're trying to track that motion. Because you have to collect images fast enough, faster than the motion itself, so that at the time of imaging, it's technically stationary for the time being. That can be done though, and the most recent advances are actually in Swiss synchrotron. A lot of images are coming from Swiss synchrotron. Shell in Amsterdam and Imperial College are doing a lot of images that is actually trying to track the motion on the pore scale in sandstones. So those are some exciting new advancements. However, they have to collect so much data that these images are huge. Right? All right. So I'm going to skip talking more about this, but if you want to look into or more about artifacts that you can have if you don't do a good sort of geometric alignment within your machine, then that can be some things to look into. Okay. And then finally, normally the best results are let's say that this is a core and I'm actually interested in imaging this portion within. The best is if you have actually physically core cut to this size. But that can be a problem as you're trying to increase resolution, because you have to have a very fine drill bit that can core something that is like maybe 3 millimeters across in a rock that easily crumbles. So that can be a problem, but then you have to understand if you have the outside that you're trying to image through, that is essentially often filtering your polychromatic beam, and you have to know that during the reconstruction in order to get better images. So most often than not, it's better to have things cut to the size you're wishing to actually image. And that can change depending on the application. Okay. Okay. I will spend a little more time just with differentiating X-ray and SCM. And what do we get? Because those are the two most commonly used in our applications for media. Okay. All right. So a lot of these images are courtesy of Dr. Kitty Milliken. Have you all been to her seminar this past November, if you were the student here? Yes, do you remember Kitty? So she's SEM Biz around at this university. She has spent a lot of time imaging unconventionals, which are difficult because you have to go to nanometer scale. But basically recognizing what you're seeing in a microscopy image is non-trivial. She's been teaching, I don't think she's teaching that course anymore, but if you do manage to catch her course in geology, siliciclastic petrology, it's excellent in terms of learning how to capture, or at least what it goes into capturing these SEM images. That is classically done by petroleum geologists. So they will typically take those images and interpret them for petroleum engineers. Why I want to point that out as important is that that interpretation is often qualitative, or things are literally point counted from the image. Do we know what point counting is? No? So typically I'm going to show it on an example image here. Okay? So there is quartz here, okay? And let's say sometimes, let's say that I want to, in this image, I'm seeing this is a tight sandstone image, right? So I'm seeing a grain. The grains are nearly fused together, and what's left over of the pore space is very little. That's the black stuff. But I also have quite a bit of microporosity. Okay? Some of it are partially dissolved grains. Some of it are clays. Okay? And I do need often some extra information to know who's who. So what is done often is you throw literally, so doing this automatically, and we were going to get to that, is not necessarily easy. Recognizing where my microporosity is, where's the porosity, are those clays, are they partial dissolved grains, whatever, what it is that they are. So geologists who are looking at a lot of these, they are already trained to recognize, and they compare a lot of different ones and possibly a lot of different types of microscopy to actually compare those. So they will throw a raster of points, say 100, 200, 400, depending on an image, and they will literally point count which one of them falls into pore space, which one of them falls into solid space, micropore space, whatever other interpretation you need. That's called point counting. And they will record that result, often in a spreadsheet. So these days, software, that type of Photoshop that they use, might actually record those as interpreted. So they will just simply click, this one is this one is that, this one's that, right? So spatial points in space where they assign porosity, microporosity, whatever phases they're looking for, might be known or maybe not. Traditionally, all that is left is an Excel spreadsheet that has counts of each. Okay? And that's what then goes into also formation evaluation, such counts. Right? They might also do grain sizes the same way. Right? And so it's semi-manual or semi-automatic. There is help from software, but ultimately there's a person making a distinction between these phases. Right? The reason why I'm pointing that that's important is that traditionally, engineers are better trained in quantitative analysis and understanding these are arrays and they have values, and we can develop algorithms that can distinguish those automatically. Good algorithms happen when these two groups talk. Okay? Or somebody from one group crosses the line of separation. Right? Otherwise, there's always a lot of guessing. Okay? So the best advancements are made when you actually cross that line. So it's often for an engineer hard to take silica classic petrology. It's something that is traditionally in geology's domain. But if you do, you'll be able to talk better to your teammates. And that's what advances science, ultimately. So I'm just motivating you to not just shun it away and say, oh, I don't know. But again, a lot of it is descriptive, and that's the source of frustration. Because geology is more descriptive, and engineers, they want a number. Give me that permeability. What is it? Right? Give me the porosity. What is it? Give me a number, and I'll work with the number. But that number is not easy to deliver. Right? And you often have to kind of consider multiple sources. Okay. Long story short, let me just... so don't just dismiss this as something important. Now, unimportant. This is a very old light microscope image of a sandstone from 1968. So bear with me. But this is same cross-section shown in plane polarized and cross-polarized light. Different type of light will be refracted differently off different mineral structures because they're ultimately crystal structures. And those will then tell you about different mineralogy. So often, not only that you have to consider one image, but basically superposition of multiple images. And that's where also it takes training. So again, there's a number of, and the reason why this polarization happens is the electromagnetic wave. It has a number of oscillating electric field and a magnetic field at 90 degrees to each other, right? And basically, when you encounter different minerals, they might reflect differently, right? So what bounces off is a different wave. Okay? So this that can affect images and can be exploited to actually figure out what those phases are. Now, when we have scanning electron microscopes, we could let's actually watch this. Oh, cannot locate. Okay, I need to update this apparently. So I'll update the slides for the next time. You can have different types of signals by electrons bouncing off the surface. So it could be light or it could be electrons. Right? And in scanning electrons, so this was cross-polarized light images, and thin sections are often imaged this way. In electron microscopy, we are shooting electron beams, and they're scattered off the surface. And then you can basically detect different types of scatters off that surface, and that produces different types of images. Characteristic X-rays are commonly done, so there's an X-ray diffraction to basically do detailed mineralogy, and you will literally see spikes in different elements that you can interpret to produce mineral maps. So all of these extra signals are basically equipment that comes in with an SEM image. And then you will also see scattered not only from the surface, the top surface that you're imaging, but also from a little bit below, which is what causes this, this sort of effect of having depth, right? Now, in cathodoluminescence, basically, you will have, you can have or equip or a piece of equipment that will actually record that in addition to your regular scatter. And that can, so you have materials that naturally, upon impact of electrons, will emit additional signal, and you can capture it. Okay? So phosphorus is one of those, and if you remember the velocimetry, we're using that often even in optical imaging, just for tracking particles within an image. Okay? So that can be also employed to the sections of rock as well. So for instance, this is differences in images that you can see between the plane polarized light and cathodoluminescence, and this is all quartz. What this cathodoluminescence gives you here, look at this grain. It's this grain here. Oh, okay. Let's try now. How about that? Huh? All right. So this is my grain. Okay. And here it is. I can see history of it. This is the original fragment. These are the cements, okay, that were added over time. Cementation is something that happens over millions of years sometimes. So over those millions of years, you're going to have different mineralogical content of those cements. Okay? even though they're all gonna, in terms of, so if I'm thinking about, so once I polish that surface and things bounce off it, they will kind of, one type of imaging just bouncing off either light or electrons might just show me a similar surface. However, this luminescence of different elements within can actually give me what happened, what is the history of this grain. This one has fractured quite a bit and then healed. Some of it did not heal. Here, this one did not heal, but there is here healed fractures, cemented fractures within. If I'm interested in breaking this grain, these are precisely the little heterogeneities that will help me break it. Okay? So this is something that can cause more fracturing within, or more crushing within certain parts of the porous material compared to the others. Okay? So this is something, and this is basically the overgrowth of cements, for instance, on this one, that I can quantify if I have different type of images. If I was interested in modeling cementation as a process in a sandstone that is basically a rock formation process, then I would need images like this to quantify what is the cement overgrowth as well as type of cements. Fractures often, no matter what their scale, this is a very small scale of fractures. If they're larger, they will heal with these cements as well. And I might need to quantify that and know what the cements are, because those could be planes of weakness. Cements is what cements I'm going to have basically depends on the transport within water that is passing through. And that can be carried from far away. So basically, if I could have calcite cement show up in otherwise quartz fracturing something that is mainly quartz, right? And that can have, if I have acids and whatever, that can cause leaching along those pathways, and I need to know about these transport processes. So that's why now I think it's obvious that it's fairly hard to analyze these images, right, and quantify them as well, which is why you would often kind of spread a raster of points and see and compare the two and see what do they fall into to actually quantify those. Okay? Yeah. So you can also see here very thin features, so you can see can you see the trace through? So basically there was an initial, possibly, a grain that has basically fused with the other grain, and the pore space in between has nearly disappeared. Okay? So this is the overlaid images. Look, that's the same locations. Possibly too much information. I don't want to know. Right? Ultimately, give me where the grain space is and where the pore space is. And if I'm interested only in permeability, that might be the only thing I'm interested in. But it really depends on the application and what it is that you're trying to do, and you might need to consult this. So the point is that essentially you get a lot of textual information from SEM images that your application might require. This is a multi-element map example. So this is about 0.05 micron per pixel. This is shale. Okay. So this is different mineralogy. Okay. Mostly silica, carbonates. Okay. So then you can know what different elements you have and what different type of mineral or kerogen you might have in this. Okay? Look at this. There's nothing in this image that kind of points out that this has completely different mineralogy. And that can cause different wettability, different all kinds of properties. Okay?
And this sort of image would come from characteristic exams.
So basically, this is taken in an SEM, but all of these different images have to be taken separately and then compared. Yeah. Same thing. So this is quartz, but then knowing where this came from is again something that trained geologists typically recognizes what it is that you have. So pyrite is relatively easy to distinguish, but even when you see quartz, knowing where it came from or where it originated is known only after you do mineralogy, or you can infer only after you're doing mineralogy, because in this image you just don't see the differences. So that's something too. So traditionally, if you have a reservoir sandstone, CT images gives pretty good information. You typically have quartz, you have pore space, and if you have microporosity, often introduced by clay, it's often not overwhelming. It's not a lot of the image. However, as you get to tighter and more unconventional resources, so this is a tight gas sandstone, where microporosity is overwhelming, it's dominant. And X-ray image in this case, so this is a SEM backscatter image, right? And you can see types of microporosity and you can quantify it, at least in terms of like what is microporous, what is solid. So microporous, solid, and pore space. And if you zoom in with SEM, you can zoom into the details and actually look at these are the clays. This is quartz. This is partially dissolved quartz. This is pyrite. Okay? So you can zoom in to areas that you need to know. However, you're getting this multi-scale sort of map of nested images that become difficult to process in a computational. So this is zooming into clays. And these clays can have different, clay platelets have different orientations. Now, if I was segmenting this by point counting, you can literally segment by hand by tapping onto the image and finding out where this porosity is, microporosity, and solids. And we're going to get to trying to do this algorithmically, which is not necessarily easy. If I were to compare the two, so this is one way of saying, okay, I can have a trained user find out where these phases are, and I can create an algorithm that is hopefully that the two match. So it's an amazing level of detail that is available in SEM, but you do have to have trained or talked to a trained person who is interpreting the SEM. However, on that 2D level where you get all of the textual information, it's extremely hard to figure out what is the three-dimensional connectivity. And nowadays there is an attempt to match these SEM images to an X-ray image, right? And aid in recognizing the two. And there's actually some machine learning approaches that are attempting to do that. So here's the 3D CT image through this, okay? And this is just to compare how it looks like. It's extremely hard to see all of the thin grain boundaries are gone. The noise has essentially swallowed them. And this was imaged at 2 micron. It's quite hard to go smaller than that. If I were to identify pore spaces here, there would be small fraction of them. And that small fraction, it's hard to get connectivity across 3D. So in at this resolution, it's hard to see whether actually it connects. So you have to be sensitive to the fact that whatever it is that you image with, so this was analysis, and I had 4% porosity, and that's simply volumetrically is not enough to connect across. So I would have to somehow aid this information with those SEM images if I wanted to actually learn what the connectivity of these is in actual three-dimensional space. So those are certain limitations when you go to unconventionals or any kind of media that has a large, wide range of pore spaces that your single resolution cannot always capture. So that's something to work with. So for complete analysis, you kind of have to go back and forth and do segments of. All right. So this is just to point out, we're going to get to more analysis, but just to point out what is the different levels of information you get from different type of imaging. Okay? Right. This is a good point to stop, so I'm not going to, for the last 5 minutes, start a new lecture. Questions? Like, do we have to know all of this? That depends on your research project and whether it's important to know or whether, but I just want you to feel sort of the differences in the information you get from different imaging modalities. Your research will ultimately determine what type of imaging you need and whether the imaging you're employing is enough. Okay? All right. Stop.